Welcome, Wonder Woman of the World. This is Ilona Budapesti, Chief Storyteller of 1 Million Women to Tech. And
this is Frederick Custer, Chief Mentor at 1 Million Women to Tech. And this is the Winter of Data, week 7 now, hypothesis testing.
Exactly. We have some amazing stuff for you. I think we should jump right in. Hypothesis testing is very exciting.
The idea is we look at the data set and we have some idea. We have an idea of a question we want answered. We want to see if there's a difference between two groups, if there are some effects that are making meaningful difference or not. Let's say if salary is determined by things like, I don't know, taking 1 Million Women to Tech class, if this gives you a boost or not. Or we will look at the effects of gender.
Of course. So I think we should have probably asked you before we got started, but now we told you. Given that it's about women, what kind of hypothesis you think we will be testing today? Mm-hmm. And it is about gender. So let's get started, I think.
Yes. And I should share my screen?
Yes, please.
Right.
Fantastic.
Everybody can see that?
Mm-hmm.
Wonderful. Okay.
We have a public data set for you here. You will have the link to it in the Jupyter notebook. But you can also find this online by searching for the New York State math test results.
So there are different data sets for different years. So we are looking at a data set which shows the test results for borrowers in New York City by grade and gender between the years of 2006 and 2011. So I think New York State lets students do different kind of standardized tests in areas such as, I think, math, reading, writing, and so on, to get an idea how well the different schools are doing, how many students are proficient or non-proficient. Okay. So first we start with our standard
pandas and
imports. Yeah. So we import pandas and we import the stats library from SciPy. If you don't have either of these are links. Here are links where you can download them. And here are, so I've renamed the CSV just to New York State math results to CSV. So I read it into pandas and have a look at it. So we see there are different columns here. So first, which is called the district borrow number, I think.
Unless you live in New York, this might not mean too much, but there are many, quite many unique boroughs here.
Yes, so here we see the different ones. I think M stands for Manhattan. So I think this one is the Lower East Side, I believe. You can look them up on the internet. Then different grades, years, categories, female, male. So that's the one we are mostly interested in. The number of students that were tested in each district, grade, year, and category.
Let me just quiz everybody. So while we're talking, please type in how many girls were there in 2008 in grade 3 in Borough, Manhattan. Well, I don't know, 01 Manhattan 015. Just type in the number so that you understand what's going on. And if you're watching on YouTube, feel free to make a comment here in the chat. I'm monitoring as well.
17. Exactly. Very, very good.
Irina got it. Daniela got it. Awesome.
Fantastic. So we don't get these scores to the individual students, but we get the mean score in each group, like 675 for grade 3 girls in 2006 in this district, And we get also both the absolute numbers and the percentages, which were in 4 different groups.
And if you look up how New York State does this, see, I don't want to spend too much time because I'd like to get into the hypothesis, but they assign these bands, 4 bands. Level 1 is basically insufficient skill. Level 2 is below expectations. Level 3 is as expectations, and level 4 is above expectations. And I think this roughly goes up to 800, the score itself, but we will take a look at that anyway.
Yeah, it depends a little bit on the year, but
also these are mean scores, so they won't go as high.
Exactly. So some outliers are already removed here. But the goal, so this is something that educators will use, or politicians will use to make sure as many as possible are level 3+4. So they are very interested in this rightmost column.
For those of you who are watching on YouTube, would you please type in the city and country that you're watching from? I'm just curious if there's anybody from New York or somewhere else. All right, let's continue.
Okay, so let's look at the unique entries in the grade column. We see we have 3, 4, 5, 6, 7, 8.
And all grades.
And we have all grades. The problem with all grades is this is an aggregate of the others together. And for hypothesis testing, we ideally want independent observations, so we don't want overlap. So if we have something like that, which is a total of all the other categories, we want to remove this. So with the year, we see the years are 2006, 7, 8, 9, 10, 11. That's good. There's no overlap here. And similar for the district borough numbers, lots of them isn't really relevant unless you live in New York and are doing policy there. Okay, but we see this format is a bit difficult to work with because the 2 categories we want to compare, female and males, they are put into different rows. And ideally we would want something which
has them side
by side in different columns. Let's say we're interested in a mean scale score, this one here, and we want to have the female score next to the male score and use district grade and year as an index. And we can do this. In Pandas, this is called as a so-called pivot table. So basically, we move this one here from these categories here from the rows to the columns. That is something you will often do if you want this kind of comparative data analysis where you have 2 different groups that you will compare against each other. So we do.
Have you done pivot tables before, either in Excel or via code? Can you type in, if you've done it via Excel, just type in a little X. And if you've done it via code, you can type in a little code. If you've never done pivot tables, you can just write no. And welcome to
Jeff Snow and Pooja from Tokyo and India.
Well, the other way around. Drifsno?
From Tokyo, yeah.
It's from Tokyo. Feel free to type in a name that you would like us to call you. And Pooja Sajnani, welcome. If there are good data sets in your locations, like in Tokyo, probably there are pretty good data sets. Or depending on where you are in India, maybe you could redo this exercise for your own location.
Yeah, 2 people have used pivot tables before, Irina and Viti.
Awesome. Hi,
Hello. Awesome, then you're already familiar. And so this is how you would do it in Python. So this will be our index, district, grade, and year. This will be our columns, the category, so female versus male. And the values will be taken from the mean scale score. And we remove the ones where the grade is all grades because we want independent observations. And we also will drop everything which has missing values. So this is what we get here. And now we can look at the head. So we see actually category female male as the columns as we want it. Then we have what is called a so-called hierarchical index, where we first have on the highest hierarchy level the district, then the grade, and then the year. And here we can nicely look at these kind of pairs.
Okay, time for test, ladies and ladies. please tell us what is the difference between the mean score. So I expect you to type in a number. Let's say, shall we say, year 2010, grade 3. What is the mean score difference in year 2010, grade 3? Go ahead, type that in, and in the meantime, we can continue.
8, says Daniela. Do we have other
takers?
Options? 8, yeah, exactly, that's correct. So 8, and in this case, the girls are 8 points better on average. And
sometimes the boys are better.
Yeah, occasionally this happens. This is probably a statistical fluke. Let's see. So here we can now quite nicely plot histograms of the score distributions, female versus male. We use this alpha value to plot them both transparently, and we see the two distributions seem pretty close. So just by eye, it would be difficult to say which one is better or not. So there's not a very clear separation between them, which is where math comes to our rescue.
Hi, Fatima. Could I ask Vicky and Daniela to turn on their cameras if they are comfortable? That would be so nice to see your faces and your reactions.
Awesome. Okay, so let's look at the difference between the two. So female minus male scores.
Fatima, please stay. It was so good to see you.
And compute a histogram of that. So this is now the difference, girls minus boys. And again, we see something which seems fairly centered around 0. It can get up to...
Again, so this is above there we have the complete distribution, the absolute, well, the values, and here we have the difference, right?
Mm-hmm. So here, these are cases where the girls are better. These are cases where the boys are better. And so just by eye, in most cases, there's no difference.
Mm-hmm.
So just by eye, it's difficult to say if there's a meaningful difference between the two.
Okay.
So let's save this difference in a separate column.
Mm-hmm.
And let's see what is the mean difference.
I just can't get over it. It's just so elegant to have these column by column operations. All right.
It's very convenient, yes. So now let's compute the mean difference among these groups. And we see, oops, on average, girls are about 1 point better. That's nice, but the question is, now, is this a statistical fluke, or is this actually a meaningful difference where we think it's quite unlikely this is just due to noise?
So I don't know if everybody knows the word fluke. So can we use a simple word for that? If this is
this
real effect, or is it because of errors?
Like if you I don't know, throw a coin 4 times, sometimes we got 3 heads and 1 tail, but then you wouldn't necessarily say, oh, that's a fake coin, because sometimes you get just 3, just out of randomness, sort of 3 heads and 1 tail.
Insignificant, that's good.
But if you, let's say, flip a coin 1,000 times and you get 999 heads and 1 tail, then you would probably think, that's much more difficult to chalk up to chance, right? So we're trying to get a more formal way of describing that. Is this something which could happen just because out of chance, because we have some noise in our data, or is it something which actually seems a real robust effect? Does this make sense? Insignificant, yes. Is it significant or insignificant? Yes, and to look at that, we can compute the so-called standard error. For that, we use the stats library, stats.sem, standard error of the mean, of the differences. And we will get something which is much, much smaller. So this means...
Is this a library that everybody would have, or if you get an error, then you might just have to go look and install it?
Yes, so I've given, up here, I've given the
link to it.
The link where you can download it if you don't have it. Most Python distributions will contain SciPy, especially if you look for scientific Python distributions. Otherwise you can. Oh, actually, I used the wrong link here. Let's correct this. Please. Cancel.
We can do that later.
We are correct that,
yeah.
Correct that, sorry.
I just wanted to ask, can we ask Vishnu from Tokyo, Japan, and Pujna Sagnani from India, as well as those on the Zoom call, if you were able to follow us in the previous classes and run any of the code that we went through. If you did, can you give us a little thumbs up in the chats? It'll be excellent. We can continue in the meantime. I just wanted to get a little feeling for it.
Okay. So, and now if we divide the mean difference divided by the standard error of the differences, the ratio is something which is called the t-value. And this is something which is, if there was no difference between girls and boys, and also if we have some additional assumptions that we can make, that both girls and boys are, the scores of them will be distributed normally according to Gaussian distributions around their respective means, then this would follow a so-called t-distribution. But if we have enough observations, as we have here, this t-distribution will be almost the same as a standard normal distribution, which has mean 0, standard deviation 1. And where will be typical values where will the values that we get in such a standard normal distribution typically lie? What kind of range will you usually see in an experiment?
This is the same t-value we looked at in the summary statistics.
Mm-hmm. We had this also for when we looked at the
summary data.
When we looked at the regression analysis, I think there were t-scores for different regression coefficients in week 5.
Plus minus certain percent around the mean 0.
Mm-hmm.
What we call exact numbers is then yellow.
Yeah, that's very, very good. Exactly. So I think we will, in 68% of cases, we will have something between -1 and +1. In 95% of cases, we will have something between -2 and +2. Occasionally, we'll have something between -3 and +3, or maybe in extreme cases, -4 +4. Something like 17 would almost never happen. So you could draw millions and billions of observations, you would never get really something that high. So this already is a strong assumption. This is already a strong indication that this may be this may actually be a significant difference. Even if it's only 1 point.
But because the error is 0.05 points, therefore this is quite a robust difference.
Okay. Notice that by forming the difference in this way, the nice thing is we can perform a like against like comparison, where we have girls in a certain year, in a certain grade, in a certain district versus boys in a certain grade, in a year in a certain grade versus district. And this means we can do a so-called paired analysis, where we have samples which only differ in the variable we are interested in, the gender, and are otherwise the same. Now, if you had which is actually good, because some of these effects may have, some of these variables here may have effects that we cannot easily model. For instance, we may have some districts which are poorer than others. So if we had only girls from Manhattan versus boys from, I don't know, the Bronx, that would be
it would be
a more difficult comparison. If we only had girls from year 3 versus boys from year 7 and so on, then we have how students may develop during puberty and all kinds of times. So these would all be confounding factors which would make the analysis more difficult, and which mean we would need a very strong sorry. We would need to see a very strong difference before we could say this is going to be statistically significant. Whereas this is ideal, such a really paired comparison where we can actually compare like with like, because then a lot of these effects will sort of be cancelled out if we look at the differences.
Yeah.
Okay. And now to give this introduction and now to make this a bit more statistically formal, let's say, let's first drop all missing values from these differences, and then we can, from our data set, I think we already did this, and then we can do what is called a parity test, or it's in SciPy stats, it's called the t-test underscore rel function, where we compare the female scores versus the male scores, and we get a test statistic. And oops, we see this is actually exactly the same statistic as we computed here. So here, in practice, you would probably just use this. You wouldn't actually calculate these yourself. You could just use this formula and be done with it. But now you see where it comes from. So we get this value for the statistic, and we get a p-value, which is if there was no difference between girls and boys, how likely would it be to get such a huge value of 17.6? And it tells us it would be extremely unlikely. So 3 times 10 to the power of minus 69, so basically negligible. And an alternative, so here we compare females versus males. And alternatively, we can directly look at the differences and check how likely it is that the mean of the differences is 0 or not. And this is what is called a one-sample t-test. This is this function here, t-test one sample. And here we put in the differences rather than females and males separately. And the hypothesis that the mean is 0. And then we get exactly the same statistic and exactly the same p-value. The advantage of here, we could have some kind of hypothesis, actually females are 2 points better than males. And then we could
Can we do 1 point? Because that's what the...
Yes. I mean, currently, it's a bit dubious to test for a value that you're observing from the data yourself. So we looked at one, we saw it is 1, and now we put in 1. So that's a bit cheating. But if before we looked at the data or from a different experiment, we would have had an assumption that it's 1, then we would be sort of more justified to use this test to test for that. So here you're not supposed to put in something which you actually looked at your data and got from. That's a bit overfitting. But if we have some sort of prior assumption, okay, we want to check if girls are 1 point better on average than 0, then we say, okay, now we get something which is much closer to 1. So here we get a t-statistic, which is now minus 0.58. And the p-value is 0.55. This means if we ran the sampling process many times, then we would get in about 50% of cases, we would get a statistic which is about that high or bigger. So this we couldn't rule out based on so this hypothesis we couldn't reject of if the mean was 1, but the one that the mean is 0, this is something we can quite conclusively reject, at least for this particular data set, which is girls and boys in New York. Okay, everything clear so far?
Yeah. In the meantime, I had a little conversation with Pooja. She's from Mumbai. There must be millions and millions of women in Mumbai. I thought of, she wished us to reach the mission, which I really appreciate. And then I thought probably, you know, if one video went viral in Mumbai, we would reach the mission.
Yeah, we can have a look if we can find more data sets, similar data sets from all around the world.
I would love actually, I would love for the viewers, whether you're watching live or the replay, is to take these as examples and then run it for your own localities. We are just demoing the process for you to enjoy. And then if you would like, you can submit them back through the datathon. Yeah. And this way share with each other.
Yeah, so data availability may differ. So I think in the US, New York is very good at releasing data. I think Seattle is very good, Chicago as well. But even in the US differs, like not all cities will have these initiatives that they make these data public. So yeah, we can have a look. Maybe we can find more data sets all around the world, but let's see. The main principles will be the same. Getting the data in all of these analyses is often the hardest part. And I don't know, well, testing people and getting money, it's difficult to teach that in a systematic way.
Viti, is it possible for you to mute yourself? I'm not able to do so. Thank you.
Thank you, Billy. Okay, just as a little aside, so we see this T statistic, if we have enough observations, if we have enough groups, should be almost normally distributed. And just to get another intuition of how unlikely such a value would be, such a big value would be, this here I computed 1 million random, normally distributed random numbers with a mean of 0 and as a standard deviation of 0.054. And so here I plot the histogram, and we see a value of 1 and so on practically never happens. Actually, amongst a million observations, it doesn't occur at all. So this shows this is just another thing.
1 or 17? 1. Oh, because 17 times. Yeah, got it.
Because they already, if I hadn't.
The mean was 17 times larger.
Yes, because I already multiplied with the standard error here. Exactly.
Yeah.
Okay. So the other thing is, can
we just go back for the intuition? So if a difference of 1 point were at all likely or possible, then there on the X value, we would get something at number 1. And we see that by 0.2, they practically disappear.
So here I check, is among our 1 million observation random numbers, one which absolute values is bigger than 0.96 or smaller than minus 0.96. And we see that's not the case. So we can rule this out, that this is due to chance. Even if you flipped your coin, let's say 1 million times, then you would never see something like that. So this means it's very, very unlikely due to chance. It's basically impossible. So girls seem to be a little bit, but statistically significantly better than boys in math, at least in New York.
It's also interesting because these are mean values again, right? So it's
ideally you would want to do this for the individual students. However, it might be a bit difficult to get the values, probably because of privacy reasons and so on.
Because there are so few people in each.
Yeah. So this is why there are the aggregates. Also, this is what these data are mostly interesting for politicians, and I think they're not interested in individual students. They want to see how good on average the students are in certain districts and grades, to see if there are some schools which would need more money, more teachers, and so on. Okay.
Which, by the way, doesn't seem to always correlate with the results. If you read The Tyranny of Metrics by a very interesting professor, he makes an argument that in the past 30 years, public investments have not correlated with this result.
That's a different problem.
Yeah.
Just going back to one thing. So we said we would, so we were quite lucky because we had this paired comparison. Now, if paired comparison, where girls and boys only differed by gender, but they had the same grade, district, age, year.
Yeah.
So if we had independent samples, like we had a bunch of results from girls, but we have maybe some girls from year 8 from 2005, but then we only have boys from year 7 from 2009 and so on. So where we don't have this nice pairing, then we would have to do an independent t-test. So that is called t-test _int. And because we may have all these kind of other confounding factors, in this case, we get a t-statistic, which is much lower. So instead of 17, it's just 4.3. And the p-value is much higher. So now it's 1 times 10 to the power of -5, which is much, much higher than this one here. I mean, even in this case, we still see a significant effect, significant difference between girls and boys, but the significance is much, much lower. So having paired observations is better if possible.
What I enjoy about this is it could be very easy for someone who wants to confound the public to say, well, there's only a 1%, sorry, not even 1%, there's only a 1 point difference between, let's say, the test scores of girls and boys if we publish something like this, and say, oh, that's that's nothing because there are 800 points in the test. But here we see it is significant no matter how we look at it.
Well, there are 2 different words of significant, and there's sort of a colloquial sense, which means significant is important.
Or big.
And then you would say, yes, it may not be like a mass, it's probably not a massive difference. And the other one, which is the statistical interpretation, which means it can be explained away by chance. And these 2 are different. So you can have a difference which is sort of significant in the sense it's big, but it could be caused by chance, especially if you have few observations. And you could have something which is actually quite small. And I would agree. So 1 point difference is not, if somebody wrote a newspaper article saying, science proves girls are smarter at math and so on, then I would probably say, 1 point difference, is this really like significant in the colloquial sense?
Yeah, but because we start out with I think we have, in society, we have sort of a hypothesis that girls are not as good at math than boys. Yes. And then you see this in the numbers. It's actually very nice and very encouraging.
So this is definitely not supported by these numbers. Definitely. Okay.
We are into the Q&A time. So anytime actually you have, because you're live, you're welcome to put in your questions. I think we can do one more section about this one.
Are there urgent questions, or can I show you something else?
Or even suggest, actually I would love to take just a breather and ask everybody who is watching, Pooja, Krishna, Fadime, Irina, Daniela, Viti, to type in perhaps what it is that stood out for you most so far. What is it that stood out for you most so far? And while we're waiting for you to type in your observation, I think we can do one more.
Okay. So this t-test is very nice. We get very statistically significant results. However, something that has to be kept in mind. It carries, and it's something which people will often use in practice when they compare different groups, like biologists will use it if they compare different kind of, I don't know, plants with fertilizer, without fertilizer, and so on. But it carries the assumption that, let's say, the scores of both girls and boys are normally distributed around their respective means. And also it carries the assumption that the variance of girls and boys is the same, and they only differ in their means. So these are relatively strong assumptions. Mm-hmm. And if we're looking at how the scores actually differ, so it's not terribly far away from a normal distribution, just eyeballing it. However, it is probably not really a normal distribution. We get some outliers here which are bigger than would be expected. We get a certain skewedness, so we are much more likely to get something which is much lower than the, let's say, median, than being much larger than the median. So can we actually do a more robust test which doesn't assume anything, which is not as powerful, which means it can only detect effects that are relatively strong compared to a t-test, but it's sort of more widely applicable because it doesn't make any assumptions. And the simplest thing we can do is we look at the number of cases where the girls were better than the boys. We call this FB, females better. The number of cases when they were equal. Okay, we sort of ignore them from the analysis because these don't tell us anything. And the ones where the males were better, MB. And we see, okay, we had 11,046
cases where the females were better.
Okay.
1,206 where they're equal, and
yes.
8,495 where the males were better. So we ignore the ones that are equal.
And now the idea was, if there was no difference between girls and boys, and this is sort of true whatever their distribution is. This doesn't assume normality. It can be like anything, but just assumes if girls and boys were equal. Now, in how many cases would you just get the girls being better and the boys being better? Well, they should be about the same. It's like flipping a coin. In each case, you would just flip a coin.
So this is another way to test the hypothesis without assuming that we have a normal distribution.
Exactly. It doesn't assume normality. It just assumes what happened if girls or boys were, let's say, equally distributed. But it could be any kind of distribution. It could have long tails. It could have skewness and so on. Because in each of these cases, okay. We also have some comments that we should
I think I'm
address.
Still waiting. Yes, we received it from Daniela and Irina. Thank you. I'm still waiting for Fadime and Viti and Pooja and Dripsno from Tokyo, Japan's comment. What was most valuable or most outstanding for you so far today? But let's do this. So if we didn't assume normal distribution and we just looked at in how many cases are girls doing better versus how many cases are boys doing better, we would expect these two to be equal.
About equal. Well, they were probably not exactly equal, but we can see it as like flipping a coin. So we now ignore the ones where they were equal. They don't really tell us anything about the differences. But we just take the cases where the females and the males were better. And the sum, we call it N. So these were like 90,500.
So about 20,000 observations. And then what we look at is what if we tossed a coin that many times?
So this is, you may have heard about that in school. So the binomial distribution tells us if we flip the coin, a perfectly, let's say, honest coin, so which gives tails and heads with a probability 50%, 50%, and flip that 19,541 times, then we will get a certain number of heads And we repeat this experiment 1,000,000 times. So 1,000,000 times, we will flip a coin 19,451 times and record the number of heads in each of these experiments, right? And this will be so-called binomial distribution. But if we actually plot it here in a histogram, we see something which looks quite surprisingly normal. Actually, we'll get something which is almost perfectly normal if our n here, so our number is of flips, is just big enough. And we will see something which will usually lie between 9,500 and, let's say, 10,050, right?
Sorry, could we go back for a second? So n is the number, this 19,541.
Mm-hmm. So on average, we would get something like n over 2, right? So on average, our number of heads would be,
n divided by 2.
Would be n divided by 2, which is 9,770.5. This is like the peak of our distribution here.
Mm-hmm.
And but then we get a certain variability. And the question we are currently assuming is, if we just flip the coin 19,541 times, could we just by chance expect 11,046 heads, let's say? And we see actually the number of heads which we will get will lie between, let's say, 9,500 and a little bit over 10,000, but it never goes up to 11,000. Even if we repeated this experiment 1,000,000 times, but even in 1,000,000
chances
experiments, this now doesn't happen. So the chance for something like that occurring just by chance is less than 1 in 1,000,000.
Fantastic.
And this didn't assume nothing except what would happen if there was no difference between girls and boys. So even under these very, very weak assumptions, we can rule this out.
Fantastic. I'm going to ask Frederick to stop the screen sharing so that I could share the screen. And then I think, fantastic. So,
I thought I stopped sharing it, didn't
I? I'll take over the screen sharing.
I clicked on something that said stop share.
I wanted to say one thing. If you are watching and enjoying, we are a small nonprofit and social enterprise, and we just got approved by YouTube recently to receive donations and also what is called super chat. So if you enjoyed it, please go to the chat section, and here besides the emojis you will see a new icon called show your support for 1,000,000 Women to Tech. And if you send a super chat here, you can make a donation depending on where you are. You know, I think sending roughly the equivalent of a meal in your country is a nice small donation. So please go ahead and do that if you can. Now, the other thing that I wanted to say is, Irina, did we already post a question about the random numbers?
Yes, you did.
Ooh. Do you have a link somewhere? I'd love to demo that, or you could demo that for us.
From what social media you wanted? From what social media?
Any and all. So we have a little fun exercise going on. If you would like to, even if you cannot donate money, you can donate, so to speak, 200 random digits between binary digits, and we will show you a cool experiment this week about them. So if I go to our Facebook page, maybe.
I sent you an Instagram link.
Awesome.
It's the most active so far.
Awesome. Okay. In the Zoom chat?
In Zoom.
In Zoom. Wonderful. Fantastic. So ladies and ladies. Oh, thank you. We have a
Why?
Esther Stefanski's. Oh, Congrats on the milestones. Hi, Silaya. Yes, yes. Oh, great to see you. Thank you.
Pooja is inspired by girls being a point better than the boys. That's fantastic.
Yes, exactly, Pooja. Isn't it? Like anytime somebody tries to tell you girls aren't good at math, you can just point to this data set in this YouTube video and be like, that doesn't, they're out by the data.
Doesn't work?
It didn't work. I think it didn't like the dash part. Let me just try. What's the dash at the end? I can also just go to Instagram/1minute to tech, right?
Yeah. And I will give you.
I think I found us.
Oh, I found it. There was
Oops,
something.
and I closed it. Instagram/1NWTT, not S, 1NWTT. Sorry.
MSTT is cute fingernails.
Yes. So here, hypothesis testing, right?
No. Below.
Pick a random number. Here it is. Excellent. So here is your challenge, should you choose to accept it, is comment with a string of 200 ones and zeros that you think is random. Okay?
Yeah, we want to see like the intuition. If people write down something that looks random to them, how random is it really? How random are you? It's sort of like a nice psychology test.
So something like this, grab your mobile and your phone and try to be as random as you think it is good. I don't know how much is 200. We just keep going.
It doesn't have to be exactly one.
Yeah,
200.
but the more the better, basically. So it's, it's however you feel like going at it. Okay, and voila. And we will collect these.
Yes.
And see if humans are in fact good at randomness or not.
Exactly.
That's our hypothesis. Excellent. Thank you so much, everybody. And the Women's Day sale is going to start next week. So if you are interested, we're opening 500 spots for the gold memberships. Please check out the details. Although next week we will be on our social media about it, so you can learn all the details. But if you go to 1millionwomentotech.com/gold, you can read about the details. And the Monday classes are open, but for the rest of the week, we will be talking to you DIYers. So Daniela, this week and next, well, this week and then 2 weeks from now is for you VIPers. And then we will poll everybody in the open community to see what request there is, because we will run an all open class for the last session of winter data. All right. Be amazing, and we will see you tomorrow.
Amazing. Bye-bye.
Bye.